Hello, in this video we're going to take a look at Gaussian elimination, which is a process or a strategy to get a matrix into row echelon form. So remember, we have a matrix that corresponds to a system of equations, let's say over here, and our goal is to make it look like a matrix in row echelon form where we have one along the diagonals, sometimes those are called the pivot positions, and a zero everywhere below it. Now notice when we do this process, the numbers that are above these ones are almost never going to match the numbers that were over here in the corresponding original matrix. So everything's going to change in the matrix when we do this process. By the way, these subscripts here just tell you the position of each entry. So A11 means this is row 1, column 1. This here, A12, means row 1, column 2. Down here, in the bottom right corner, we're in row 3, column 3. Okay, so this is our goal. Remember, the reason we're doing this, if we go back to a previous slide, is if we can get a matrix in this row echelon form, we can actually read the solution right from the matrix. For example, this tells me that 1z is equal to 4, so I know z is equal to 4. And as we saw in a previous slide and video, we can then use that value of z in the equation right above it to find out what y is, because y plus z equals 6. But if I know what z is, then I'll be able to solve for y. So that's the reason we're doing this. If we can get it into this form, we can read the solution off pretty quickly. So our goal now is to take some general augmented matrix and put it into row echelon form. The way we do that was with 3 row operations. There's only 3. The first one says that we can swap any 2 rows. Right? And of course, if we do that, 2 rows are affected. And so we change 2 rows from the original matrix that we start with. So for example, we could just take row 1 and swap with row 2. And here's the symbol we use, double arrow. Now, if it had more than 2 rows, we could say swap row 1 with row 5, or swap row 3 with row 4. It doesn't matter. Pick any 2 rows you need to swap, and then you can do that. The second one is to multiply any row by a non-zero constant. I don't have that typed here, but we should make a note that multiply by a non-zero constant. And then replace that row with that multiplied row. So only here, in this case, only 1 row is affected here. So for example, if I take row 2 and multiply it by 1/3, every single term in that row is multiplied by 1/3, and then put that back into row 2, then only row 2 is changed, and therefore row 1 and any other rows below it won't get altered in any way. So those are the first 2. Those are relatively simple. Hopefully you can see how that's not going to change the solution to the system. This third one's a little less intuitive. It says we can add a row to the multiple of another row. In this case, only 1 row is affected. Let me show you the notation here. What we're doing is we're replacing row 2 with itself added to a multiple, a non-zero multiple of a different row. So in this example, we take -3 times row 1, add it to row 2, and that whole result gets put into row 2. So 1 row, row 2, gets replaced. And that will not change the solution to the system. So that one's a little bit harder to see why it works that way, but trust me, that works out just fine as long as you do the arithmetic here. We'll do an example here in a moment, but those are the 3 row operations. There's only 3 of them. Anytime you start engaging in this Gaussian elimination process, you're going to use one of these row operations at a time. So here's the process that we're going to undertake. First, we're going to get the first row in the upper left position to have a leading value of 1. Next, we're going to use one of the 3 row operations to get zeros below that leading 1. So this is really important. You go 1 column at a time, left to right. We start with the first column on the left. We put a 1 up here. We use row operations to get this to be a 0. Then we use row operations to get the number below it to be a 0. Once we're finished with that column, we then move to column number 2. Right? We then move to this second row and make this position a 1. So now we're working in column 1. We can ignore what's up here. We only need the 1 along the diagonal. So we would use whatever row operations we need to get this to be a 1. And as soon as we're done with that, we stick with this column, column 2, and we get the entry below that to be a 1. Excuse me, to be a 0. Right? So we use row operations again to get this to be a 0. And then we continue this process until all of the leading positions in the rows, in other words, the diagonal entries are 1s, and all of the 0s are below them. The numbers above the 1s don't really matter. If it turns out that a row becomes all 0s, just move that row down to the bottom of the matrix. It doesn't contribute in any way to your solution. So let's take a look at an example. Let's solve this by Gaussian elimination. 4x plus 3y is equal to 11. X, or 1x minus 3y, is equal to -1. Now obviously, this is a solution, or excuse me, a system that you could solve with either substitution or the addition method. And that's normally how we would do that. But let's go ahead and use this elimination process so you can see how the process works. And then we'll move to situations where we have 3 equations and 3 unknowns. So our first step is to take this system of equations and write the augmented matrix for it. So up here, the first equation is 4x plus 3y equals 11. So I have a coefficient of 4, then a coefficient of 3, then a coefficient of 11. The second row is 1x minus 3y is equal to -1. So I have a coefficient of 1 for x, -3 for y, and -1 for the constant term. That's our first step. Okay, now we want to make this upper left corner, this first row's leading position, to be a 1. It's not a 1. The easiest way to do this is to simply swap row 1 and row 2, because row 1 already has a 1 in its leading position. So what we'll do is simply swap row 1 with row 2 using this notation. You always want to write what you're doing between steps, and we'll get this. So we just swap the rows. It just changes the position of each equation, no problem. That's the easiest way to do it. Note, you could have, if you wanted, you could have multiplied this 4 by 1/4. But that's kind of dangerous because you have to do it to every single piece of that row. So you have to multiply 3 by 1/4, giving you 3/4, and then 11 by 1/4, giving you 11/4, and then you will have introduced fractions into the matrix. And we are going to avoid that at all costs. Don't do a row operation unless you can get integer entries. In this course, you should always be able to do that, and so that should be something to keep in mind. Okay, let's keep moving. We have 1 in the upper left corner of our matrix. Now what we want to do, again, as I said, moving column by column, we want to move down and make this a 0. Swapping rows won't do the job because A, this is not a 0 up here, and it will undo what we just did in the previous step. We can't multiply by a non-zero constant and get this to be 0. So the only thing we have left is the third row operation, which is to multiply row 1 by a -4, then add it to row 2, then replace row 2 with that result. So here's what we're doing. We're taking -4 times row 1 plus row 2 and adding it to row 2. Now, why -4? Remember, we're trying to make this a 0. So if I add to this a -4, it's going to make this a 0. The way I can get a -4 is by coming up to the leading 1 position and multiplying by some number to get what I need to add down here to get to a 0. So of course I have to multiply 1 by a -4. And that will give me the -4 that I need so that I can add it to this one here, and that will give me 0. So let's just put a -4 over here because it tells me I'm going to multiply -4 by row 1. And let's see what the results look like. Keep in mind, we're just changing row 2. Row 1 doesn't change. So you can literally just copy it here. These 3 entries in row 2, we're going to do one at a time. So let's work on the first entry first. So here's how it works. We take -4, that constant, times this entry. Sorry, -4 times this entry is -4, plus the row below it is going to give me 0. So that's how I get this 0. Now, to get this entry here, I'm going to do -4 times -3 is +12. +12 plus 3 gives me +15. And then the last piece, -4 times -1 is +4. +4 plus 11 gives me another 15. So now I have 1 up here with zeros below it. I'm done with this column. I can now move to the next column. The next column over here, column 2, I want to make this a 1. I don't really care about this anymore above it, this -3. I'm focused on making this 15 a 1. So that's our next step. Now, remember, we have 3 row operations. Once I've made the top row or the rows above it have 1s, I really don't want to start swapping those because then you're going to mess up that work. So I only have 2 operations available to me. Multiply the second row by a non-zero constant, or do row operation number 3, right? But you can see here that the easiest way to get this 15 to be a 1 is to simply multiply it by a constant, and that constant is 1/15. 1/15 times 15 gives me 1. So that's what I'm going to do here. I'm going to take row 2, multiply it by 1/15, and put the result back into row 2. So I'm just replacing row 2 with a constant multiple of itself. And when I do that, when I multiply that 1/15 by every single entry in that row, I'm going to get 1/15 times 0 is 0. 1/15 times 15 is 1. And then 1/15 times this 15 is also 1. Now notice, I am now in row echelon form. I have 1s along the diagonal, and I have 0s below any leading entry of 1. And so I'm done. It doesn't matter what's up here, at least for now. What matters is I have this in row echelon form. So now what I can do is solve the system with back substitution. Notice that this second row, and we always start with the bottom row when we do this because it's in the form that we need it. We have 0x plus 1y is equal to 1, which is the same thing as saying y equals 1. Then, because we know that y equals 1, we can take that result and put it into the top equation, which is 1x minus 3y is equal to -1. We see here. Because y is 1, we're going to put it here. Right? So x minus 3 times 1 is equal to -1. Solve for x and we get x equals 2. And so there is my solution. X is 2, y is 1. Now, when you go to write this up, it's going to look something like this. You'll start with your original system of equations. You'll show your augmented matrix. And then one step at a time, you will show which row operations you do to get from one step to the next. Notice I'm swapping row 1 and row 2, and then I show my result over here on this side. Then I take -4 times row 1, add it to row 2, and put that into row 2, and that gives me this one here. From here, I take 1/15 of row 2, and I put that into row 2, and that gives me my row echelon form. Then I use basic substitution and a little bit of algebra to find my solution and then box it like normal.